Hello and welcome back to today's video. In this video, we're going to talk about the matrix representation of linear mappings. So that's today's topic, matrix representation of linear mappings. Now, the idea of this section is the following. You have already seen that each matrix induces a linear mapping. And that is just defined by saying X maps to A times X, where A is the matrix. That induces a linear mapping between two R to the M, R to the N, R to the something spaces. Now, a natural question to ask is, can we kind of revert this? Given a linear mapping, is there a matrix such that it can be written in the form X maps to A times X? Or under what conditions can we find such a matrix? And in this section, we're going to investigate this question. So again, the idea here is if we have a mapping, a linear mapping of a specific form, namely f of x equals A times x, for a matrix A in R to the m by n, this is a linear mapping. And specifically, it's a linear mapping with the domain R to the n and the codomain R to the m. So the question is, can we represent every linear mapping in such a form, or under which conditions can we do that? So can we represent a given linear mapping in that form? Now, to answer this question, we'll have a look at an example first to get an idea of what might happen here and how we could compute such a matrix and when this is actually possible. So, as an example, we'll have a look at a mapping that is defined on the domain R to the fourth. And the codomain, let's say we'll take R to the third. And of course, we can't define that mapping using a matrix. That would defeat the purpose. But we will define it by defining the images of a basis. So we just take the canonical basis of R to the fourth and then assign values to the images of that basis. We've learned before that a linear mapping is uniquely defined by prescribing the values on a basis of the domain. And that is exactly what we're going to do here. So that will be defined by the images on the basis C, C for canonical basis, and that is simply the basis that consists of the unit vectors u1, u2, u3, u4. So the unit vectors are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Let's define that by prescribing f of u1, and the values given here are really just arbitrary values that we want the function to take on these basis vectors here. So the first value that we will have is 1, 0, 1. The second value, 0, 1, 2. And finally, the third and the fourth value. -211 and 3 -1 -1. There's nothing special about these values. That would work for any choice of values. Now, if you prescribe this, we can, of course, compute the image for an arbitrary vector in R⁴. So, for V in R⁴, and V has a form V1, V2, V3, V4. We have f of V equal to well, of course, this V1, V2, V3, V4 can easily be represented as a linear combination of the basis vectors. And the linear combination is simply V1 times U1 plus V2 times U2 plus V3 times U3 plus V4 times U4. By linearity of the function f, we know this is the same as V1 times f of U1 plus V2 times f of U2 plus V3 times f of U3 plus V4 times f of U4. And we know the values of f of U1, U2, U3, U4. Remember, we prescribed those when we defined the mapping. So this is exactly the same as f of U1 is 101 times V1. I just changed the order. Plus f of U2, that was defined to be 012 times V2. F of U3 was defined to be -211 times V3. And finally, f of U4, 3 -1 -1 times V4. And easy enough, this can be seen as a matrix vector multiplication. If we just write those vectors here as columns of a matrix, like this, then we can write this expression as the multiplication of this matrix and the vector V1, V2, V3, V4. So in a way, we could say this matrix here is a representation of f of our linear mapping. So indeed, f can be written in the form matrix times vector. Now that is all fine, but there's one problem here that we'll have to address. And that is our choice of basis. We choose the canonical basis for pretty much one reason, because it was easy to work with. That allowed us to come up with this linear combination here very easily. And of course, that linear combination is the V1s, V2s, V3s, V4s. Had we chosen a different basis to define f, we would have to compute the right values here for that linear combination, and that might have been some work. In other words, we would have to come up with the coordinates for some other basis before we can do the following steps. And of course, those choice of coordinates might influence the actual result. So this whole thing depends on the choice of basis or on the choice of coordinate system. And that is not just true for the domain. In a way, that's also true for the codomain, because the outcome here is again a vector, and of course that vector of numbers, in this case in R3, that could be represented as coordinates into some coordinate system. In this case, we'll also choose to interpret as coordinates in the canonical basis, but that is by no means necessary. We could choose a different coordinate system for the codomain. And of course, that might change the outcome. So this matrix here, this depends on the choice of basis for domain and codomain. Here, we used the standard basis for both. But in general, once we fix these bases for the main and codomain, we can pretty much do the same steps, and we can obtain a corresponding matrix. And that is exactly what is known as the matrix representation of a linear mapping. I will summarize that in a theorem. So in order for that to work, we'll again need finite dimensional vector spaces because we want a finite basis, because as you have seen, every vector in our basis here corresponds to one vector in this representation, so one column in the representation. And of course the same is true for the codomain. Every line here corresponds to a dimension of a codomain, if you want. So we want finite dimensional vector spaces to be able to come up with that matrix. But that is pretty much the only restriction on this. So let V, W be finite dimensional vector spaces. And we'll just say, for ease of notation, the dimension of V will be denoted by n, and the dimension of W will be denoted by m. Furthermore, let B and B bar be coordinate systems for V. So B is a coordinate system for V, and VB bar is a coordinate system for W. And of course, that opens the door to this matrix representation even for linear mappings between abstract vector spaces. So if we have some R to the n, R to the m, then of course we can always choose the canonical basis and we can use that as a coordinate system. For other vector spaces like polynomials or things like that, we introduce a coordinate system and then we work with coordinate vectors, and those are again elements of Rn and Rm, so we can nicely work with those. Okay, so here we have our coordinate systems for V and W. Now let's say we have a linear mapping. So if F, V to W is a linear mapping, then there exists a unique matrix. We call that matrix A. That is an element in R to the m by n, such that the following holds. And that's a condition that holds for all vectors V in the domain capital V. And what we need here is, if we compute the image of V under F, And then of that image, take the coordinate vector with respect to the coordinate system in W. So remember, this is contained in W. So what we have here is a coordinate in B bar. So this is the B bar coordinates of the image of the vector V. And remember, you can always think of V being R to the N, W being R to the M, and then just take the canonical basis. Then the vector itself, the image itself, is equal to its coordinate vector. But for the general case, we'll need those coordinates here to get actual numbers. And the statement is the coordinate vector of this image is equal to 8 times the vector V, or better, the coordinate vector of V, this time in B coordinates. So V is, of course, in capital V. So these are the B coordinates of the vector V. So you can actually represent that linear mapping F by this matrix A if you switch to coordinate vectors. So you can't expect to multiply general vectors with a matrix. General vectors might also be something like linear mappings or polynomials of a certain degree or things like that, and you can't multiply those with a matrix. But you can, of course, compute the coordinate vectors. And using coordinate vectors, using coordinate systems, we can get all of this into the spaces Rn and Rm that we used to. And in these spaces, there is such a matrix representation. Let's continue this with a definition right away. So that matrix A, that is called matrix representation of the linear mapping F with respect to the coordinate systems B and B bar. And as you can see, that's also in the name. So, of course, this matrix representation will depend on the choice of both of these coordinate systems. It is usually denoted by a similar notation as for the coordinate vectors. So for this A, we'll use the notation F. We put that in brackets. And then we put the coordinate systems as indices here. And we'll use the coordinate system of the input. We'll put that as a subscript on the right. And for the output, we'll put it as a subscript on the left. So what that means is we usually multiply the input vector to A on the right. Yeah, so the input into this linear mapping is the vector V, and we multiply the input vector or the coordinate vector of the input vector on the right of the matrix A. That's why we put this B here on the right. And then the output can be processed further. So what we imagine is the input moves through the mapping and then out of the mapping, and it comes out in terms of B bar coordinates. So this is the reason for this strange notation. As a quick summary, we could say something like the columns of this matrix are the images of the basis vectors of B. So Each vector in the coordinate system B, in the domain coordinate system, corresponds to a column of that representation matrix. And these columns are meant as coordinate vectors with respect to the coordinate system B bar. So the columns of F, B, B bar are the images of the vectors in B given in B bar coordinates. And just as a side note, you'll encounter different notations for this matrix. So this here is by no means standard notation. There is no real standard notation here. Something that you'll often see is a notation like M of F for the matrix representation of F. And then those B and B bar are often either in this form here, as Indy says, or sometimes in this form here, which is kind of ambiguous. That's why I prefer the left and right index here. But that's largely a matter of taste, of course. We'll usually denote the canonical or the standard basis consisting of the unit vectors by C. We did that already. And of course, if V and W use the same coordinate system, then it's often just denoted once. So if V equals W and the same coordinate system is used for domain and codomain, we abbreviate that notation a little. So instead of writing it this way here, we only write the B once, and in that case we write it on the right hand side. Okay, now that seems a little abstract, I know, so let's have a look at a few examples to illustrate my case here. Let's consider R2. And we'll use R2 for both domain and codomain. But we use different coordinate systems. And we start with the coordinate systems B for the domain, and that is 1, 1 and minus 1, 1. And B bar for the codomain, and that is 1, 2 and 2, 1, just as an example. Then we define a linear mapping. Let's call it F on R2 and mapping to R2. And we'll define it by the images on the basis vectors in the coordinate system B. So we'll just say F of 1, 1 is defined as 1, 2. F of minus 1, 1 is defined as 2, 1. Now, that of course is intentionally simple, because what we get then is, if we work in these coordinate systems, then remember the coordinate vector of 1, 1 with respect to B is 1, 0. And the coordinate vector of -1, 1 with respect to B is 0, 1. Right? But we don't actually have to know that. What we need to know are the images of those basis vectors. So these here are the images of the two basis vectors. And those images go into the columns of our representation matrix. So the images of the basis vectors of the domain, remember those from the columns of the representation matrix. This one here. But we must write them in B bar coordinates. So we cannot put those vectors right away in the columns. What we want is their B bar coordinates. So we take 1, 2, and we want the B bar coordinates of 1, 2, and of course, well, this is a vector in B bar. It's the first one, so the coordinates of that vector are precisely 1, 0. And same thing for the second. So the vector 2, 1 has B bar coordinates 0, 1. So those are the vectors that go into the representation matrix then. That means FBB bar is 1, 0, 0, 1. Right? So this is how we construct this matrix. Now, what about the case where we have such a matrix, like this here? I want to change one of the bases. Let's do that. So let's say, what about, let's say you want to know, we want to use the matrix C, the canonical basis, we want to use that in the codomain. I want to keep B in the domain. And again, C, the canonical basis is U1, that's 1, 0, and U2, that's 0, 1. Or let's rather write this way to emphasize the order. So how do we get that? Well, again, we know already the images of the basis vectors f of 1, 1 and f of -1, 1. Remember those were 1, 2 and 2, 1. And what we need is we need their coordinates with respect to the new bases in the codomain. So what are the codomain coordinates of 1, 2? Well, with respect to the canonical basis, 1, 2, that's 1 times U1 plus 2 times U2. The coordinates are therefore 1, 2. And here, the C coordinates of 2, 1 are of course 2, 1. So what do we get? Well, we get the matrix representing F with respect to B and C is the matrix composed of these two columns here. This is 1, 2 and 2, 1. And remember, this here is the image. So F of the first basis vector in C coordinates. And this here is the image of the second basis vector in C coordinates. And now finally, let's go one more step. And let's say we want to compute the matrix representation of F with respect to the canonical basis in both domain and codomain. what do we need? Well, we need to compute the images of the basis vectors, and now the basis vectors are 1, 0. So we need the image of 1, 0. We know the images of 1, 1 and of minus 1, 1, so we'll have to get back to those values. And to this end, we have to represent 1, 0 through the vectors 1, 1 and minus 1, 1, because we know the images on these. So we have to find the linear combination such that this is equal to 1, 1, and we can just use 1 over 2 and minus 1 over 2 here. So this here, if you look at that, this is exactly equal to 1, 0. And that means this image, f of 1, 0, is equal to 1/2 f of 1, 1 plus minus 1/2 f of minus 1, 1. Well, we know f of 1, 1 is 1, 2. And we know f of minus 1, 1 is 2, 1. So together with the coefficients, we get the vector minus 1 over 2 and 1 over 2. So this is the image of 1, 0. And we can do the same thing to obtain the image of 0, 1. Now 0, 1 can be represented as 1/2 times 1, 1 plus 1/2 times minus 1, 1. So this here is exactly equal to 0, 1. And that means we get 1/2 f of 1, 1 plus 1/2 f of minus 1, 1. So this is 1/2 times 1, 2. And 1/2 times 2, 1. So what we get here is 3 over 2 and 3 over 2. Now we need those images in C coordinates. So of course the C coordinate of minus 1 over 2, 1 over 2, that is exactly minus 1 over 2, 1 over 2. And the same holds for 3 over 2, 3 over 2. C coordinates of that one is exactly the same, 3 over 2, 3 over 2. So here's our matrix representation, FCC. The first column is the image of the first basis vector, so that's minus 1 over 2, 1 over 2. And the second is the image of the second basis vector, 3 over 2, 3 over 2. So this is the matrix representation with respect to the standard bases in both domain and codomain. Well, this completes this introduction. What have we achieved so far? We have seen that there is a way to represent a linear mapping by means of a matrix, such that the mapping can be expressed as f of x equals matrix times x. To do this, we had to define coordinate systems on the domain and the codomain. And basically, the matrix then works on the coordinate spaces. And of course, that also means that the matrix itself will depend on the choice of coordinate system. It will change if you change one of the coordinate systems. This completes the introduction into this matrix representation. In one of the next videos, we'll then ask the question of how we can change the bases or the coordinate system in an easy way. In this case, we basically repeated all the computations, but there is a way to represent this as a matrix multiplication, and we'll go deeper into that topic in the upcoming videos. And as always, I'll be happy to see you there.